This video is on errors in precision. Here are the understandings. Question 1. Define random error and give 2 examples. Random errors usually occur when the person taking the measurement has to determine the last significant figure when reading an instrument. Random errors can be in both directions, meaning our measurements are both too high and too low from the correct value. So examples are limitations of the measuring instruments and limitations to human reaction times, like using a stopwatch. Question 2. Define systematic error and give 2 examples. Systematic error usually occurs when there is something wrong with the instrument. Systematic errors are in one direction only. Our measurements are too high or too low from the correct value. So an example is a scale which measures mass does not begin at 0. This is called a zero offset error. Or a metal ruler on a hot day will measure objects to be smaller than they actually are because that metal ruler gets longer. Question 3. Determine if the following errors are random or systematic. So 3a, parallax error is systematic. Now parallax error means your eyes are not parallel to the level of a liquid or a ruler when measuring the height of that object. Part B, zero offset error. So this is a systematic error. This is a problem with the instrument. It's like if your bathroom scale doesn't start at 0, you're always going to be off by the same amount. 3C, a meter stick which does not begin at 0 is a systematic error. So imagine you're measuring the length of something and you're always starting at like 5 centimeters. You're not starting at 0 centimeters. So if you're always starting at 5 centimeters, whatever you're measuring, it's going to be too short. Because if you start at 0 centimeters, it's going to be too long. So if you actually start at 0 centimeters, your solution is going to be shorter. 3D, a slow running clock, that's a systematic error because you're always going to get a lower time than what's actually happening. 3E, measuring the time for a leaf to reach the ground using an accurate stopwatch. That's a random error. Because if you're using that stopwatch, sometimes you're going to have a time that's too high, sometimes it's too low. Question 4, define accuracy and give an example of high accuracy and low accuracy. High accuracy means measurements are near to the correct answer. Low accuracy means measurements are not near to the correct answer. And you could see these 2 examples. Low accuracy means your measurements are far away from 9.81 meters over second squared when calculating the acceleration of gravity on Earth near the surface. Question 5. Define precision and give an example of high precision and low precision. High precision means measurements are near to each other, to the same value. Low precision means measurements are not near to each other. So, you could see high precision doesn't mean you're going to get the correct answer. High precision just means you're always getting the same answer. So even if you're getting the acceleration of gravity consistently to be 9.81 meters over second squared, that's high precision. Question 6. Below are a set of dartboards. An X on a dartboard represents a measurement. Mark 7 measurements on each dartboard, which shows low precision and low accuracy. So on the left, you have low precision, low accuracy, meaning the values are spread all over each other. High precision and low accuracy, you could see the measurements are all very close to each other, but they're far away from the center being the correct value. Part C, low precision and high accuracy. As you can see, low precision and high accuracy means if you take the average value of all of these measurements, you're going to get the correct answer. But you never once reach the correct answer. And finally, high precision and high accuracy, you could see the values are all very near the center. So high precision and high accuracy means you're always getting close to the actual value. Question 7. List the rules with regards to determining the uncertainties in measurements for analog and digital instruments. So this is something you need to memorize in yellow. The uncertainties in non-digital instruments are always half the lowest measurements possible. So if you have a ruler with 1 millimeter divisions, you have 0.5 millimeters as your uncertainty. Now, the uncertainties in digital instruments are always the lowest measurement possible. So look at the first example. The uncertainty of a digital or electronic stopwatch with a division of 0.01 seconds is 0.01 seconds. Question 8, state the equation and give the meaning of standard deviation sigma. So you could see the steps taken to get to the equation for standard deviation. You don't need to memorize these steps, but just understand what is highlighted in yellow. The standard deviation is a measure of how spread out the measurements are. If the standard deviation sigma is large, then the measurements vary greatly. If the standard deviation sigma is small, then the measurements do not vary greatly. Question 9. What is the equation to determine the uncertainty of many measurements? Delta x is the uncertainty. It's going to be the maximum value that you measured minus the minimum value divided by 2. So for question 10, it tells you to determine the mean and uncertainty of the following time measurements. So first, to determine the mean, you just sum up all values, divide by 10 to get the average, 2.302 seconds. And delta t is the uncertainty. You take the maximum value minus the minimum value, divide by 2. So this is our solution here. 2.3 plus or minus 0.1. Now, the reason why the uncertainty is only one significant figure is because that's just the rule. The uncertainty is always one significant figure. And the reason why the value is 2.3 is because where the significant figure is at, which is at the tenths, the value of the average should be ending at that value. So it's going to be 2.3. So 0.3 is at the tenths, 0.1 is at the tenths. Question 11, calculate the absolute uncertainty, fractional uncertainty, and percent uncertainty for a measured length of 87.65 plus or minus 0.43 meters. So remember, we're looking at the uncertainty. So we're only looking at the 0.43 for the most part. The absolute uncertainty is 0.43 meters. Fractional uncertainty is 0.0049. We take 0.43 divided by 87.65. And the percent uncertainty, we take the fractional uncertainty and we multiply it by 100%. Question 12. Use a pencil and ruler. A displacement versus time graph of an object moving with a constant speed in a straight line is given below. Draw a best fit line. Estimate the slope and y-intercept, and finally give an equation of the speed of the object in the form of y equals mx plus b, which is equivalent to displacement equals m times time plus x initial. The squares have a vertical unit of 1 meter and a horizontal unit of 1 second. So imagine you get a graph that looks like this. You have an object moving to the right, and you're measuring the distance the object is from the origin, x equals 0. So you have all these measurements. What we want is a best fit line. So there's two rules you need to remember. You want to get the number of dots above the best fit line to be equal to the number of dots below the best fit line, or the number of values. And you want to have the best fit line cross as many values as possible. So here we go. The number of measurements above the best fit line is equal to the number of measurements below the best fit line. Try to have as many points on the best fit line as possible. The best fit line can also be a curve. So that word line is a little bit deceptive. Okay. All students will give different solutions, and the best fit line doesn't need to pass the origin. So this is a best fit line that I drew. Now my value is going to be different than your value. So how many dots do you see above this line? 1, 2, 3, 4, 5, maybe 6. How many do you see below? 1, 2, 3, 4. So could this best fit line have been better? Yes, but this is just an example. So the problem tells us to draw a best fit line, and that's what I did. And you could see this best fit line pass through a few points. And now let's take 2 points on this best fit line to find an equation. So one value is one point is approximately 0, 3, another one is about 3, 5. So we could use those two values to find the slope. Then we could use y equals mx plus b to find an equation for this best fit line. Once again, the equation for this best fit line will be different than yours. And great news, Microsoft Excel can make a best fit line. So you could go to any search engine like startpage.com, type in Microsoft Excel best fit line, and there's many websites which teach you how to draw. There's many websites which tell you how Microsoft Excel could give you a best fit line.